Hello everyone, my name is Kovalev and I'm glad to present you our work, Hyperdimensional Representations in Semiotic Approach to AGI. This work is done with my colleagues Evgeny Osipov and Alexander Panov. The outline of today's talks is as follows. First, I introduce you to visual question answering task, when we discuss the basics of cognitive architecture, sign-based work model, and vector symbolic architecture. Then we combine these two architecture and apply it to the visual question answering task, show how it works on model example, and discuss future work in that direction. So what is the visual question answering? The problem here is as follows. Given an image, we have to answer questions to that image. And this example from the VQA dataset, and you can see that images are quite complicated and as well as questions. For example, we have to answer such questions as how many slices of pizza are there, or is this a vegetarian pizza? To be able to answer to this kind of questions, agents have to have common sense knowledge and have to have reason about this knowledge. But this is not the only setting in VQA. Another very famous dataset is Clever, and it's called a diagnostic dataset, and this is purely synthetic data that generated from 3D scene. While the images are much more simpler, so with limited number of objects and like type of these objects, questions are still very difficult, and there are some examples as are there an equal number of large things and metal spheres? And if we want our agent to answer this kind of questions, it has to understand what's the equality mean, what the number mean, large, metasphere, etc. And even more, it has to solve the simple grounding problem when we have to link internal presentations of these objects to the sensory data, to the data taken from our environment. Now let's talk about cognitive architecture, sign-based work model. This architecture stores knowledge about objects, processes, and relations of external environment. Also, it represents internal parameters of intelligent agents. It also includes procedures, how we can operate with knowledge, how we can acquire them, and how we can perceive, reasoning, set our goals, and plan our behavior. This model based on psychological concepts of human brain functioning. And the main component of this work model is a special structure, what we call sign. Sign is a special structure that has 4 components. Significance, what is like the common knowledge, what's shared among the group of our agents. Meanings, what the agents obtain while it's operating in the environment. Name is just fine string, so like the name of the sign. And this is a symbol in its like pure form. And then there is such a component as an image, and this is what refers to the symbol grounding problem. So how we can link this name, this like symbol or this whole sign with the raw sensory data. And here is how these components are represented. For this we use a special structure, what we call causal matrix. And I apologize. Okay, here is my mouse. Each column in this matrix is a time step, and in simplest form, this matrix is binary. And if you got a 1 on this position, it means that in this particular time step, some exact feature has appeared, and then we can call this an event. And with this structure, we can represent 2 types of entities, objects and procedures. But if you want to represent the procedures, we have to split these columns into 2 parts, what will represent causes and effects. But in this talk, we will focus just on the representations of objects, so we don't need to worry about this splitting into two subsets of columns. And how it works more concretely in our settings. Given this image, our system has to detect its component, and if we detect in particular order, such as shown here, we first detect left eye, then right eye, then nose, and then mouth. And when we obtain this matrix, which represent the image component of a sign that is a head. But these concrete parts can be recognized in different order, and then we get another version of the same image. And even more, we can construct a causal tensor. Then the third dimension is number of precedents, how we can recognize these parts like in different order. And like say more generally, given an image like sensor signal, picture that in this example, we have some feature structure but get these parts, and then this becomes the images of special signs. In this example, it's like left eye, right eye, nose, mouth, and maybe some other signs could be. But these images, parts of another image of another sign, what is head, and head is part of image, is part of sign, what is body, and thus this forms a causal network, or this special kind of semantic networks, and forms some kind of hierarchy. And if you want to talk about sign-based but more generally, we can say that each of these components form its own semantic network, or causal network to be more concrete, and together with linking functions, special functions, what allows us to go from one component to another, and applying this special compositions of these functions. If we get a stationary point in this case, then we say that this stationary point is a sign. And then we can think about this four networks as one network that composed of signs, and we call this network a semiotic network. Okay, now let's move to vector symbolic architecture. A vector symbolic architecture attempts to combine two approaches, symbolistic and connectionist. In symbolist approach, we can operate with symbols, and in connectionist approach, we usually work with vectors. So, in vector symbolic architecture, each concept, variable, or attributes represented as a high-dimensional vectors, and in simplest form, this is a binary vectors. How to say it with high dimension, about 10,000, or maybe it could be even 1,000. And there are like several operations with these vectors, which we discussed later. But the interesting property of this architecture that if we sample a random vector from this hyperdimensional space and fix it, and then start to sample another vectors and measure the normalized Hamming distance between this fixed vector and just sampled one, then this distance will be centered around 0.5. That means that 0.5 means that they are orthogonal. And if we increase the number of dimensions, then this part has become narrower and narrower. And then we get about 10,000 dimension, about 10,000. Then 99%, about 99%, will be quasi-orthogonal to this fixed vector. Quasi-orthogonal means, so it's the distance between these vectors not exactly 0.5, but it's very close to this value. And this helps us to encode objects, like concepts, variables, attributes, just with random sampling from this hyperdimensional space. And now how we can operate this with kind of vectors. First of all, this like operation is called binding. This is just multiplication. And we can use it if we want to assign a value to some attribute. We just multiply these vectors like element-wise. And there's like undo operations. If you want to encode some special data or time data, we can use permutations, or more concrete, cycles shifting. We just, if you represent the state of some system like at 0 time with x0 vector, when at the next time with t is equal to 1, we can represent this as a shifting by one position this vector. And if you want to represent the set of objects, we can use just bundling operation, and this threshold sum. And like exact property of this operation that the resulting vector y will be closer to these vectors that in this sum than to the others vectors. Now we attempt to combine these two architecture and apply it to visual question answering. First of all, now let's think that each of these column is just a special attribute. Let's call it AI. Then we can say that sorry, just lost this part. We can say that if there is one appears in this column, then this attribute get this value with j, and we can say then that event is just assigning a special value to the special attribute, and we can use binding in this case. Then we can encode the whole matrix as a set of these events, and as we work with objects, not procedures in this time, we don't have to worry about like the splitting into causes and effects. And even more, now we can get rid of this third dimension, if you remember, causal tensor, with dimension of precedence. Now this is just one high dimensional vector. Then if we bind this high dimensional vector with its name of this sign, it will be represented again as a high dimensional vector, we can get this Cm prime vector that will be used in the higher level of abstraction in our causal network. And each of these attributes and value are stored in a special data structure that's called item memory. And it's we use it for two purposes. First, of course, we store just these versions, like clean versions of this vector. And then we can search the closest vector given a query vector. And how it works. During some operations, we can obtain like the noisy version of some vector. Let's call it AY. And if we search the closest vector, we can gain the clean copy of this vector. Okay, let's apply it to real but model example. Given this kind of image, where we have 4 objects with different shapes and color, we want to encode the whole scene as a one hyperdimensional vector. And we can do it as follows. First, we represent each object as a set of its attributes and values. So in this case, object 0 is represented as a set of 4 attributes: color with value gray, shape with value circle, and x and y coordinates. Then the whole scene we can represent as a set of these objects that are represented in this scene. And now let's assume that the task is to extract objects that to the right of the object 3, with this given object. How we can do it? First, we have extract the exact position of this object, and we do it just by applying binding operations with scan vector and like the name of this object, the object 3, and we want to get its position, so we have to bind it with this placeholder, this attribute x. Then they get this noisy version of vector x1, so this is here, and just for simplicity, like referring to this, the position of the third object, let's call it x3. After that, we pass this noisy version of vector through the item memory, and we obtain the clean version of this vector. Then let's form a bundle with all possible coordinates to the right of x3, and we do it by shifting our given clean version on 1 position, 2 positions, and up to n positions, and n is like hyperparameter, depending on our assumption how many objects can be on this picture, and we obtain this bundle. Then we can bind this bundle with a scan vector, and we obtain the noise version of vector O1 about this vector. And if we pass this through item memory, we can get exactly this picture. Then this noise version of this vector will be closer to the version to the vector of object 1, and we can see this. And in such a way we can answer the questions. So what objects are to the right of the object 3? But as you can see, this task is very simple, and in future work we want to apply these approaches to more difficult tasks such as a clever dataset. And now we have to form like another pipeline, like more difficult, more sophisticated. We want to apply our approach to more complicated tasks such as clever dataset, and for this we need more sophisticated architecture. So first we have to detect objects on our image and encode them in hyperdimensional vectors, and we can do it by like traditional networks such as autoencoders or random Boltzmann machines. Then using classification we can get the attributes and store these attributes in item memory. After that, this data passes into scene representation. This is our like sign-based word model representation of a scene, how this structure works. And after that we get this vector that represents the whole scene, and this vector is passed to reasoning engine. On the other hand, our question also could be encoded as a hyperdimensional vector, and this representation also fits in the reasoning engine. And in the end, our reasoning engine uses these two representations to obtain several particular actions and return the answer to the given questions. But this is the part of like our future work. And that's it. That's all what I wanted to say, and thank you for your attention.